which one's the laser?
Back.
Okay. Can everybody hear me if I move my head around while I'm talking? Is the mic close enough to me? Okay. Okay, thank you. So today I'm going to be talking about what direct imaging and particularly from optical through the thermal infrared can do for our understanding of extrasolar planets. I'll be using BetaPic as a demonstration example that we've recently observed with our AO system. And I'm talking in detail about using the Magellan AO system, which we have just finished commissioning. We spent 2 months in Chile over the past year. The PI of this system is very close. We have a visible light camera that goes from R band to 1 micron, and Jared Males is the built and commissioned that camera. And we have an infrared camera, Clio, which goes from 1 to 5 micron, which I'm commissioning. So Jonathan gave us a great introduction this morning showing that with the spectrum from 40 years ago, we had already started to learn a lot of details about Jupiter's atmosphere. Here's a temperature pressure profile showing the inversion and the different cloud condensation points. So we actually have a really detailed picture of Jupiter today with a globally and annually averaged energy balance plot that gives us a good picture of this planet. Of course, we're all here to do this for exoplanets, and the picture is a little more complicated because a range of planets can give us a range of spectra, and there are all the different condensates depending on the temperature pressure profiles, and the composition of the planets can give a range of cloud features. And this is just equilibrium models. Then there's non-equilibrium and patchy mixed clouds and everything. So that's what we're here to work on today. In fact, and then the models themselves vary in their treatment of opacities, abundances, clouds, metallicity, chemistry, and dynamics. So this is an example of the VLM and ground dwarf MLT sequence. And you can see all the range of models that have been used to fit different parts of the sequence well, but it's been challenging to find something that can really explain everything about these observations. Looking at what we can get from a longer spectral coverage from about 0.5 microns out to 10 microns for planets of a range of effective temperatures, you can see all the different information from in the optical out to the infrared. So a recent example of this work was done by Andy Skemmer at the LBT, which is a similar AO system to the Magellan AO system, where he imaged the IAU299 planets for the first time at 3.3 microns and found that the models were too faint. And so you can see that there's actually, for this example of equilibrium and non-equilibrium models, there's actually a lot of action going on in the 3 to 4 micron regime. And so what Andy has now done is he's gotten a series of 6 narrowband filters at these wavelengths, and he's imaged the planets in each of those filters. And I encourage you to go to his poster and see what he can tell you about his mixed cloud model. Another example is the companion to ABPIC, which we have recently imaged with the MEG-AO system. This is work by Kim Ward-Dong, Jenny Patience, Rob DeRosa, and their group at ASU, where they have I, Z, and Y band imaging with VisAO, and 3.1, 3.3, L, and M band imaging with Clio, which goes together with their Symphony near-IR spectra to give a more complete picture of this object. And I encourage you to see their poster to hear more about it. Okay, so MEG-AO is on the 6.5 meter Magellan Clay telescope here at Las Campanas Observatory in Chile. The team of instrument builders consists of people from the University of Arizona, from Arcetri Observatory in Italy, and from Carnegie Observatories. And the system is a modulating pyramid wavefront sensor, natural guide star, and we go up to 378 modes and up to 1 kilohertz. Our limiting magnitudes is down to 14 in R for the short wavelength science, and we've closed as faint as 16.5 for the thermal science. We have an adaptive secondary mirror with 561 actuators at a pitch of 23 centimeters. We have modal gain and selectable subaperture size via pixel binning. This is an image of the adaptive secondary mirror being raised out of the polishing chamber. And here's a picture showing the the panel at the telescope when we're controlling the system. This is the pyramid pupils. This is the control commands to the DM. And here is a picture of the star, which is a binary. So MEG-AO has 2 co-mounted science cameras. So we get our light from the ASM, and then we have a beam splitter and send the infrared light to CLIO, whereas the visible light is split between the pyramid wavefront sensor and VisAO, the visible camera. Having co-mounted cameras allows us to do simultaneous science that other instruments aren't able to do. And VisAO has an 8x8 arc-second field of view and has an imaging mode and a spectral differential imaging mode. And CLIO has 2 cameras, one with a 16 arc-second field of view and one with a 28 arc-second field of view, and has imaging modes, non-redundant masking, aperture, phase plate coronography, and prism. And to see more about this, if you're interested in observing, please check out our website, megao.as.arizona.edu/observers. So just a little bit more about VisAO, R to Y, H alpha, sulfur and oxygen SDI imaging. So here's some of our performance on Sky. So this is an image from the tower, basically our lab testing. And on Sky, we're getting very similar PSFs with the control radius and the core. So CLIO, again, remember from J all the way out to M, and with the NRM and the APPs. First, let's look at the theoretical PSF to compare CLIO's performance. So here I've imaged both the ASM, which has 4 thin spider arms holding it up, and it has a slot that was cut here to prevent a crack from spreading. And then I also have the cold stop, which has 2 thick spider arms holding it up. And so you can see the theoretical PSF has both the diffraction off the cold stop spiders and off the ASM support spiders. And so to compare our model to data, this is a model without wavefront error. And our data, this is 3.3 and this is 5 microns, is showing very similar PSF to the model. And so these speckles here on the area rings aren't so much atmospheric speckles as they are interaction between the cold stop spiders and the ASM spiders that you see here. So MEG-AO is the newest member of the extreme AO systems around the world. I'm plotting here wavelength coverage against the spatial sampling of the AO system with the turbulence on Sky. And so we can see at the longer wavelengths, MEG-AO is indeed an extreme system, as is LBT. All right, so now I'm going to move on to talking about our recent observations of beta PIC. And Mikhail Butterfly gave a really excellent introduction to this, so I'm glad I don't have to go through all the details. So I can just start by showing you our images from this is from our first commissioning run in the fall. So here's the PSF of beta PIC and the model. And here's the planet that I've gotten out by doing angular differential imaging and principal component analysis reductions. So the 3.3 micron image again with the model. And so this is the PSF of beta PIC, and here's the planet. And so L prime, here's the PSF of beta PIC, and here's the planet. And finally, 3.1 microns, again, the PSF and the planet, and you can see a hint of the disk. Then we also have on the VisAO camera Jared's results, which are very exciting. Here's his PSF of beta PIC, and here's the planet that he's reduced in Y short at 0.98 microns. This is the first ground-based detection on a CCD of an exoplanet. And he's getting excellent contrast down to 10 to the minus 5 at a half arc second. I encourage you to go see his poster, number 1.23, to find out more about the details of his reduction in contrast analysis. So here I have in total our images of beta PIC simultaneously from 0.98 to 5 microns. I'd like to point out a few things here. First of all, the simultaneous cameras allows us to give it some of the systematics in astrometry. So this Y short image was taken on the same night as the M prime image. And so we're able to cross-check our astrometry to verify our measurements. And that's one of the tough measurements in exoplanet imaging, is figuring out the astrometry of the primary star. And then also you can see just as the PSF gets bigger and bigger as we go to longer wavelengths, so you can see that shorter wavelengths is also giving us a really interesting spatial sampling and contrast there. This is a very preliminary plot of our photometry for those on YouTube. I'm still working on confirming and verifying this. In particular, but we do see that our optical point is continuing the trend of being brighter than the models. And then here are my thermal IR points. One of them is quite a bit fainter than the model, but as Mikhail noted, their group has been doing 2 pipelines, 4 algorithms, what do you say? So, and they do 2 different methods of subtracting the planet to get the photometry, and they have 7 different models they compare it to. So they explain in great detail what they're doing, and we're also trying to go to that level of precision to ensure our photometric accuracy. So that's why this is preliminary. Okay, and then what else can we discover from beta-PIC? We also saw that the initial entropy estimates depend on the assumption of the formation model, and then that impacts the mass, and that ranges the mass go from 6 up to 13.7 Jupiter masses. There's a recent paper by Bodenheimer that is models of core accretion, but using having the actual accretion onto the envelope causing shocks and giving a high initial entropy, so that you can get little bursts that give a 13.7 Jupiter mass for the beta-PIC point, or a 10 Jupiter mass for a hot start. These models by Bodenheimer are also showing luminosity peaks during accretion shocks onto the core. And so that's another interesting thing that we're imaging with MEG-AO. So with VisAO, we have the H-alpha spectral differential imaging camera, and I'd encourage you to see Larry Close's poster, number 1.11, that shows how our H-alpha contrast gives us a much better sensitivity to these types of accreting planets than some other instruments. And finally, again, with the SDI mode, Kate Follett has a poster number 3.14 where she's imaged a disk in silhouette to get the density profile of a disk in Orion, and using the SDI H-alpha mode. So in summary, so to do a detailed characterization of exoplanets, the models are crucial, but the models actually need more data because there's still so many degeneracies within models and between models, so models in their treatments and the parameters that they're using. And so we're really excited about MEG-AO, which has these unique 0.55 out to 5 micron capabilities for characterizing exoplanets. We're diffraction limited and doing deep imaging in the optical and infrared, and high contrast imaging via spectral differential imaging, angular differential imaging, and apodized faceplate. We have a 20 milli-arc second resolution at H-alpha, and we're thermally optimized for 3 to 5 microns, and giving us simultaneous visible and IR imaging. And my summary for beta-PIC is that even the mass and the age is still under question, and the atmospheric composition and the clouds, depending on the models and the photometry. So we're continuing to get more data, and MEG-AO is commissioned, and it will be available in 2014A. And follow our blog at megao.as.arizona.edu. And also, we have stickers available. Oops, sorry. We also have stickers available if anyone is interested in that. Okay, thank you.
Thank you very much, Katie, for a very interesting talk, very exciting talk. Can we start with Thane?
This is a very impressive system. So I just had like 2 very small, detail-oriented questions with the images. What is the signal to noise that you're getting, especially at Y-band? And then also, I was confused about the structure of the subtracted PSF. Like the one I think at M-band looked like a TIE fighter on Star Wars. It was,
yeah, that's a great question.
Yeah, 3.3. Yeah, sorry, 3.3 microns.
Yeah. So the photometric accuracy of the Y-short point is about 4 sigma, since we have both the Y-short and the M-band images simultaneously, the detection signal to noise is a lot higher than that, or certainty is a lot higher than that. Now, the reason why all these planets look so funny in these images is that these are just the straight PCA residuals. I haven't done masking or subtracting of fake planets or anything, and so you get basically ringing on the sides of the planet because the PCA is finding the modes that fit the PSF. And so this is trying to fit a high spatial frequency object with a low order mode, and so you're getting a little bit of ringing there. This is the artifact.
Cool. Mikhail?
Hey, excellent, very excellent talk. The instrumental strategy is amazing, and I had the chance to observe an LBT a few days ago, and just to see these PSFs with the adaptive secondary and the pyramidal wavefront sensor, it's so amazing. I'd like you, if you could just go back to the SED. I just have a comment actually. I think that the new data points you are getting in the red optical and also the complementary data points that you are getting are very interesting. I played with the metallicity, with the BT settle and the drift phoenix models, and as far as I remember, the J-band flux and the flux mainly at shorter wavelengths than 1.3 microns is dependent on the metallicity of the object. So you might be able to say a bit more about the metallicity of the object. So that's very interesting.
Excellent. Thank you so much. That's great. Thanks.
Okay, I need to ask a question if you don't mind.
Okay.
So I was really amazed the 1 micron beta pic image is really spectacular. But I was wondering about the astrometric precision. Of course, there's all this concern about what the orbit's doing. So what kind of precision do you get at that shorter wavelength?
Well, thank you for asking that. That's a really great question that we've been looking at a lot. So people don't talk about this a whole lot, but one of the most difficult things in astrometry on saturated PSFs is actually centering on the primary star. And not only is it difficult to center on a saturated PSF, but because all of these mechanisms require on rotation about a center, because we're doing angular differential imaging, it's really important to get that accurate to a subpixel fraction. And so we've been doing different methods to ensure our centering on the primary, which actually can change the position on of the planet up to 1 to 2 degrees in PA. And so our astrometric accuracy in terms of our plate scale is like about a few to 10 milliarc seconds, but in terms of the systematics in the centering and the astrometry on the planet, it's highly dependent on the centering on the PSF to like 1/10 of a pixel, so like a few milliarc seconds.
Okay. Thank you. No other questions? Okay, then we'll thank Katie again.